Good morning, student. So, welcome to Urban Pro. In this session, I am going to discuss AC circuits and transformers. Okay, AC means alternating current. Okay, so when the current, the magnitude changes, okay, alters from and its directions also changes. Okay, so let me write AC circuits, AC circuits. But what we will be do in AC circuits? See, AC circuits is nothing but what is there? A alternating voltage supply will be there. So AC voltage supply will be will be connected with what? Resistance type of things. That is the elements or current decreasing elements. Better to write current decreasing elements. For example, the current decreasing elements like resistor, capacitor, inductor. Okay, so will be connected with current decreasing elements, or better to write will be connected with one or more. Okay, so let me cut it. Will be connected with one or more, one or more current decreasing element. That is maybe a resistors only, maybe a capacitor only, maybe a inductor only, but maybe resistor and capacitor, capacitor inductor, resistor inductor, or maybe all of them at a time. Okay, so this will be the expression for current. So here we plotted along y-axis V and current I. V, that is voltage supply, by blue color, and by green color current is plotted. Okay, we will not stop here. We will draw the phasor diagram as well. Okay, we will draw the phasor diagram also. Okay, let us draw it. Let me copy. Let me move this graph. Let me move this graph to here. Okay, fine. So here the V will be here. Now we will draw phasor diagram. What is that? This is, we will draw now phasor diagram for this resistance sub-circuit. Okay, so phasor diagram. Here, suppose this is an initial line. This represents a line, the phase direction when time is 0. After some time t, let's say the voltage is oriented in this direction. Okay, so this angle will be omega t, and this is the amplitude of the voltage source E naught. What about the current? The current will be along the same direction, same phase. There is no phase difference between the applied voltage source and the current. So they will be just overlapped. But the current, the magnitude or the amplitude of the current is little less. So I keep the length of this arrow little less, and it is denoted by I naught. Okay, fine. So phasor diagram is what actually here we try to represent the current and the voltage, the amplitude of the current and voltage. So amplitude plus the phase. Here we represented the phase also. Okay, fine. Now we will draw. Here time is passes, current is flowing, voltage is being supplied. What is the change in resistance here? As we can see here, there is no change in resistance. resistance is independent of the frequency of the power supply. So if we want to draw the graph between the time and the resistance, it remains constant, so it will be a straight line parallel to the x-axis. Okay, now we discussed here resistor with AC voltage. Now we will move on to the next element, that is capacitor. When a capacitor is connected with a AC source, what is the current, what is its amplitude and all we will see. So our second discussion will be capacitor with AC source or AC voltage, as you can write. Show how the graph will look like, sorry, that's how the circuit diagram will look like. This is the current element. Suppose this is the capacitor, this is the capacitor, and a AC source will be connected with this. Sorry, a AC source will be connected with this. So this is the AC source, and we will represent it using this sinusoidal symbol. And let's say the capacitance of this capacitor be C. And what is the power supply? It is V is equals to V naught sine omega t. Okay, what we will find now? We will find now the current. Okay, see here current will be passing through the capacitor. Okay, so here induction will be taken place. Okay, see, as we know, C is equals to what? Q by V. Suppose at any time t, the charge stored in the capacitor is Q, and the potential difference across this capacitor is V. Then we can write C is equals to Q by V. From this, we can write Q is equals to CV. But we are looking for current. How to find it? Current means dq dt. We can write ddt of q, as you know. This is also a definition of current. So we will just take the derivative or time derivative of charge, that is CV. CV, isn't it? CV. Fine. And the value of the V is given as V naught sine omega t. So this is nothing but the current is, see, the capacitance C is constant, so we will take out of this derivation. So C times d dt of, in place of V, we will write V naught sine omega t. This will give C V naught. The derivation of sine omega t gives cos omega t, and a omega will be multiplied with the C V naught. So we can write it as V naught by, let me use some different color, 1 by omega c. This omega c V naught is written as V naught by 1 by omega c times cos omega t. See, this cos omega t again can be written as sine omega t plus pi by 2. Sine 90 degree plus theta is equals to cos theta, you know. Why do we write this cos omega t in terms of sine omega t plus pi by 2? Actually, we want to compare with the given voltage supply V. Here it is sine omega t, here it is sine omega t plus pi by 2, isn't it? So the phase difference here the phase difference is pi by 2. This is also important. Now, as earlier, we plotted the voltage and current in a single graph to compare. Again, we will do this here. So this is, we are going to here plot the voltage and current along y-axis. So first we will plot the voltage in blue color. It is nothing but V is equals to V naught sine omega t. Let me change it its color to blue, then it will be easier for you to understand. So it is nothing but a sinusoidal graph as we drawn earlier, and its magnitude is nothing but V naught. Here we protect V in blue color. Now we will plot what? Current. Current is what? Okay, we can write it as, you see, V naught, we can write it as I is equals to I naught sine omega t plus pi by 2. So it will be, its phase will be, uh, phase difference will be pi by 2, and it is, its phase is, I mean, it's not lagging, it's leading the voltage plus pi by 2. So its phase is leading the voltage by pi by 2. So we can see, we can directly draw just cos omega t. This sine omega t plus pi by 2, we are getting it from cos omega t. So let's plot a cos function here by blue pen, green pen. It will look how. So before going into the proper drawing, let me scale this so that we can draw a better curve. Okay. So here also, whenever we have to draw the graph, in a single graph, we are plotting two curves. So that is why the scaling is important. So we'll start here, and it will go to 0 here, and it will go to maximum here, and again 0 here, and here it will go to maximum. So this is the cos function, and it is current. Okay, so here the important thing is, here the phase difference is 0. Let me write here, here the phase difference was 0, phase difference between the voltage and current. But in case of capacitor, when a capacitor is connected with an AC, we see that the phase difference is 90°, or better to write pi by 2. Even we can write this in words like, where we'll write this, we'll write here, make a note here, that current leads voltage by pi by 2. Fine. Next, we'll move on to the phasor diagram. How to draw phasor diagram. Phasor diagram, here we consider only the amplitude and the phase, isn't it? So suppose at time t is equals to 0, this was the phase. Okay, t is equals to 0. After time t, the voltage is suppose in this direction, and its magnitude is E naught. Fine. After time t, I said after time t, so this angle will be omega t. What will be the direction of the current? As we get here, that it will, the current will lead the voltage by 90° or pi by 2. So the current will be, make an angle 90°. I have to keep the length little less compared to this voltage, as you know the reason. So the magnitude is I naught, and here let me write I naught is equals to V naught by omega c, isn't it? Sorry, not by omega c, by 1 by omega c, by 1 by omega c. Even we write it as V naught by xc, that is impedance due to capacitor. What is xc? Xc is capacitive impedance. Okay. Okay, and this angle is, as you know, pi by 2. So this is the phasor diagram for a pure capacitor in alternating circuit. Okay, now we will move on to its inductor. When inductor, a pure inductor, that is, there is no resistance, pure inductor with a AC source. Okay. So what will be the case here? The thing is, this is an inductor. This will be connected with a AC source. Let's say the AC source is V is equals to V naught sine omega t, and the inductance is L here. Here, I am not going to derive the current again. I am just writing it. I is equals to here V naught by omega L times sine omega t minus pi by 2. In capacitor, we got the current was sine omega t sine omega t plus pi by 2. But in case of pure inductor, it is sine omega t minus pi by 2. Just believe me, you have to derive. We will derive it in other classes if possible. So the current is this. Then what we do, we draw the graph, isn't it? Along x-axis and along y-axis. Along x-axis, initially we draw the voltage source. Its magnitude is E naught and the current is 90-degree lagging. So it will be like, so as you know, we always need proper scaling when we plot two curves in a single graph. Okay, so the proper scaling is important. So okay, something like this, and here it is I naught. What is the value of I naught? It is V naught by omega L. What is omega L? Omega L, it is written as XL is equals to omega L. So we can plot here with respect to time. Suppose this is time t. This is in this direction we'll plot time, and in this direction we are plotting suppose XL, that is omega L. Omega L means 2 pi f into L. Sorry, in this direction we'll plot frequency. Okay, so we'll write omega L or 2 pi L into f. Okay, so it will be nothing but a straight line passing through the origin. In case of capacitor, we can also plot it. In case of capacitor, we can also plot it like, it will look like how. Here we will plot frequency, and here along y-axis we will plot xc. Xc means what? 1 by omega c, or 1 by 2 pi f, that is omega times c, or we can write it as 2 pi c 1 by f, isn't it? From this we can also say xc times f is equals to constant. So the graph will look like a rectangular hyperbola, isn't it? Okay. So this was all about the current, phasor diagram, phase difference. Also, we can comment here that current, or current here lags behind voltage by pi by 2. Here also we have to draw the phasor diagram, how it will look like. This represents when t is equals to 0. Voltage, suppose this is the voltage E naught, and definitely this is omega t. So at that time the current will be lagging behind the voltage. So it will look like this current. This is I naught, and this angle is 90 degree. So this was phasor diagram for current and voltage for a inductor with a AC source. Okay, let us recapitulate the thing once. For pure resistance, this is the case. There is phi is equals to 0. Here phi is equals to pi by 2 phase difference, and here also pi by 2. Here also the phi is pi by 2, but it is in opposite direction. The direction is different. So this was all about AC circuits. I hope you all understood this. Next, our topic is transformer. Our next topic is transformer. So transformer, we will briefly discuss transformer. What is transformer? Transformer is a device, static device. It is a static device which transformer, that is a transfer AC, alternating energy, actually AC electrical energy from one device or one circuit to another, one circuit to another by electromagnetic induction. By electromagnetic induction. Okay, so this is what a transformer. What is the basic principle in case of a transformer? Basic principle. Basic principle in this case is, see, let me draw a simple circuit. This is a very basic diagram of a transformer. This is here a AC source is connected, and here we get the output. Okay, here we get the output, and this is input side. This side is known as primary, and this side is known as secondary. Okay, the basic principle is the current, the AC current in primary produces flux which produces or induces EMF in the secondary circuit. Okay, this is the basic. Okay, we can write using the Faraday's law of electromagnetic Faraday's law of electromagnetic induction. So this is what the basic principle. The current that is entering into the primary coil, it creates flux. That flux produces some EMF or voltage in the output circuit. So this is what the basic principle. This is the Faraday's law is used here. Here we will you have to know what are the how this voltage is created. I mean, so what is the magnitude of the voltage? What is the relation between the voltage in the input, output? We will discuss this. Okay. So the relation is the voltage relation. Voltage relation. Suppose the voltages that will be induced, suppose it is Vp in the primary, Vs in the secondary. How many number of turns are there? Suppose Np, number of turns in the primary coil is Np, number of turn in the secondary is Ns. Then the relation between them is Vs, the voltage induced in the secondary, by the voltage in the primary circuit will be equals to the ratio of the number of turns in the secondary by number of turns in the primary. So it is proportional to the number of turns. The voltage that is induced in the coil is proportional to the number of turns. Okay, there are actually two types of transformers. If suppose Ns, that is the number of coil in the secondary coil, is greater than that of the primary, then this type of transformer is known as up step up transformer. I am not writing. Okay, transformer. If the number of turns in the secondary coil is less than that of the primary, then it is known as step down transformer. Okay. Now, what is the power for ideal? Suppose we are talking about ideal transformer. Okay, we are talking about ideal transformer. In ideal transformer, the thing power. In ideal transformer, power is conserved. Okay, power is conserved. What does it mean? That is input power is equals to output power. Okay, so what is the power? We know voltage, current, so definitely from this we can write what is input power. This is nothing but power. You know, P is equals to VI. Let us write it as power in input and power output. Okay, so power input is P is equals to VI. So VS, sorry, not VS, that is VP primary, and IP is equals to VS IS. Okay. Okay. So we want now the relation between currents in the primary and secondary. Let us write it. IP by IS is equals to, we can see, VS by VP. As we already know, the relation between VS VP is equals to nothing but NS by NP. So we will substitute here. It is NS by NP. So it is NS by NP. That is the number of turns in secondary coil to that of the primary coil. So let us write IP IP by IS is equals to NS by NP. So this is the ratio of the current in the primary coil to the secondary coil. Ideal transformer. Okay. Okay. What about the uh, real transformer? That is, see, there is no ideal transformer. What will be the real transformer? For real transformer, there is a term efficiency. That is, definitely it cannot transfer all the power from input to output, from primary to secondary. In that case, it is defined as power output by power input and into 100%. For real transformer, we calculate the efficiency of a transformer. Okay, now simple numerical questions can be solved using these relations, IP by IS, and the relation between this power, this efficiency, and this step up, step down, VS VP. Using this relation, simple numerical questions can be solved. Okay, so this session was all about AC circuits and transformer. I conclude here. I hope all you understood this well. If you have still any doubt, then do connect with me using this through the Urban Pro profile, and see you in the next session. Okay, thank you.